Welcome to the second video lecture for the first week of the MPP Calculus course. This will be a quick lecture, but I wanted to devote a little bit of time to talking about the notation that different people use when they're talking about the derivative of a function. So let's start off by supposing that we have some function f of x, and we're interested in figuring out the derivative of that function f of x. And we're looking for the general derivative, not just the derivative at a single point a. Unfortunately, mostly due to history, there are at least 4 routinely used notations for the derivative. The first 2 are the ones that you're most likely to see in your Harris classes. So you might see dy dx, or another version of the same thing, df of x dx. Both are notation that was come up with by Leibniz. Very often we credit Isaac Newton with the invention of calculus. Leibniz invented it basically at the same time, simultaneously. Isaac Newton's notation is much less frequently used. You see it occasionally in physics settings, where you put a single dot above your y, or you say f dot of x to indicate the first derivative. So that's Isaac Newton's notation. You generally won't see your Harris professors use that particular notation. The other frequently used Harris notation is Lagrange's notation, which is the prime notation. So f prime of x is also could also be written y prime, although you really don't see that done very much. So that's the Lagrange notation. Don't, for those of you who are hearing other people talk about stuff, this is not the Lagrangian. Lagrange is just a mathematician who used this particular notation. Euler, that's Euler spelled like that, came up with his own notation, which is to use a capital D in front of the F. And just like Newton's notation, in Harris classes, you're unlikely to see that. Now, you might ask, why do these 2 formulations of the notation for first derivative persist? Why can't we just make up our minds about which one we should use? And the answer is a little bit of a mix of the fact that both are very widespread and that each has times when it is helpful. So Leibniz's notation is much more flexible when, in a moment, I'm going to talk about partial derivatives and the notation for partial derivatives. Leibniz's notation is a bit more flexible than Lagrange's notation. The flip side of that is Lagrange's notation is much more succinct, and you can't accidentally start treating f prime of x like a variable, versus I've seen students before make the mistake of thinking that you could, divide out the dx and the dy and treat them separately, which you really can't do. So Lagrange's notation is a little more succinct, while Leibniz's notation is a little more flexible as you get to more advanced topics. So when we take Leibniz's notation, df of x dx, basically what we're saying is we're making explicit the fact that we are taking the derivative of the function with respect to the variable x. With Lagrange, that is implied. So when you say f prime of x, it is implied that you're taking the derivative with respect to x. As we move on, you're going to see functions that are functions of multiple variables. And so Lagrange's notation stops being useful in a context where you have more than one variable. Leibniz's notation is a little less clear when it comes to taking the second derivative. So if I want to denote the second derivative of the function, It is d squared f of x dx squared, which is a little obnoxious. Basically, what you're thinking of is you're thinking of the derivative as something of an operator that you're applying to the function f of x. And so you're seeing that this derivative is happening twice, which is what this squared is implying, versus Lagrange's notation is a bit more flexible to just say f double prime of x is the second derivative of the function with respect to x. So really the upshot of all of this is simply just to recognize that if you're asked to find f prime of x, that is the same as being asked to find df of x dx. If you're asked to find f double prime of x, that's the same exact thing as being asked to find d squared f of x dx squared. Sometimes you might also see that written dy dx and d squared y dx squared. Just recognizing that those are identical things, just written with slightly different notation. Okay, so that's the first point about notation. The second point about notation has to do with a distinction between variables and parameters. And this is something that I know a few of the professors use, but many of them do not. It's something that if you end up taking any courses over in economics, you will definitely see. So when we talk about a function f of, let's say, L and K, we sometimes also want to talk about other factors that affect the function. So in this case, what I'm writing down here is a standard Cobb-Douglas production function. And we have some constant A out front. We have a variable L, which is the supply of labor, a variable K, which is the supply of capital, and then we have elasticities up here in the exponents. Now, when we talk about these, about the constant A and about the elasticities beta and alpha, very often you'll hear people talk about these as parameters. Now, what is it about parameters that makes it worth thinking about them differently? Parameters are very often the things that we're trying to estimate empirically. So in other words, if you have a data set, you often will actually know the amount of labor supplied and the amount of capital supplied, and you'll be interested in estimating the elasticities and estimating what's out here is the total production, or is the total factor productivity. So these are empirically interesting quantities. And to keep that in mind, very often you will see functions like this written as a function of L and K. And then there will be a colon, and it will say that it is a function with the variables L and K and the parameters alpha, beta, and capital A. One way to think about this is that the entity that is acting in this case, so the firm that is making a choice of how much labor to use and how much capital to use in its production, doesn't have control over these parameters. The parameters are something that are external to the firm's decision. So when the firm is making a choice, it is optimizing its choice over L and K, but it is not optimizing the choice with respect to A, beta, and alpha. These are parameters that are outside of its control. Another way of thinking about that is that when we do the optimization problem, when we ask how do you maximize this function, we need to maximize it with respect to the variables L and K, but without changing anything with regard to these parameters. These parameters we basically treat like constants when we evaluate the function. So the last point I want to make about notation is that there are also two completely different ways of writing the partial derivative. So in this case, the concept of a partial derivative only becomes useful when you have more than one variable. If you have more than one variable and you're doing an optimization problem, you have to optimize with respect to both of the variables. So you have to think about taking the partial derivative with respect to one of them and the partial derivative with respect to the other one. So in this point, that notation that we had before of f prime stops being useful. Leibniz's notation remains useful. We typically, when we're talking about a partial derivative, we distinguish it from a standard derivative by using a script d rather than a standard lowercase d. So I might be interested in taking the partial derivative of the production function with respect to the labor supplied, or, and if I'm doing an optimization problem, I will want to take the derivative with respect to the capital supply. So the script d way of writing it is really just a tweak to Leibniz's notation. And we make a slight tweak to Lagrange's notation too. Instead of using primes, we end up using subscripts. So in this case, if we wanted to find the partial derivative with respect to L, we would write f sub L. If we wanted to find the derivative with respect to the capital supply, we would write f sub K. So when your professors are writing these subscripts, they are actually talking about taking first derivatives. If you want to denote the second derivative, now notice that you'll be able to take the second derivative with respect to either L or K. So you could have, if you take it twice with respect to L, you would have script d squared f of script d L squared. If you decided to take the second derivative twice, you're taking both derivatives with respect to K, you could write d squared f and dk squared. Notice that there is a cross partial derivative that you might also be interested in. That would be d squared f, because you are still taking a second derivative, but you write it script k script L. The order doesn't matter definitionally, and we'll talk about this again when we get to talking about partial derivatives formally. It doesn't matter if you take the derivative with respect to K and then the derivative with respect to L, or vice versa. They are actually equal to one another. So now you can kind of see that this notation is a little bit cumbersome. It's helpful because it's very explicit about what you're taking a derivative of and what it is with respect to, but it adds a lot of cumbersome notation. So often economists will instead, if they want the second derivative with respect to L, just write it with a second subscript, the second derivative with respect to K, and if you take the cross partial derivative, you have f sub K sub L or f sub LK, either one of which is equivalent. All right, so with that whirlwind tour of notation, there's one more lecture today, which is about the basic algorithm that you might use to take a lot of the types of derivatives you're likely to see in class.